much for coming, and I introduce you in Spanish, but please give us more details of your.
Buenas tardes. Me gusta mucho de ser aquí con vosotros, pero no puedo hablar mucho español. So, I will now switch to English. So, I'm computational linguist, that is, I work on natural language processing, mostly on English and French, sometimes on other languages such as German or Japanese, for instance. I've been studying basic science and then computer science. Then did a PhD on, well, actually computational linguistics. That PhD happened to be in a hospital. So the texts I started to study were medical texts. At that time, reporting adverse reactions after drugs. And so I passed that PhD, and then I got a position in the hospital to do artificial intelligence, to do natural language processing research. And I continued this way, and then, well, 20 years later, I decided to move to CNRS, which is the National Research Council in France. So that's a large organization, a large research organization with all sciences again. But I was, and I'm still am, in a laboratory called LISTEN, the interdisciplinary laboratory for digital sciences. And in at LISTEN, we have a large department for natural language processing with about 80 faculty, PhD students, postdocs, working on different sides of language processing, both written language, speech, sign language for deaf people, and machine translation, and other things. And I still do natural language processing on medical text within the context of that computer science department. And I still have collaborations with hospitals in which we try to analyze the contents of patient records to try to help medical doctors do their job better. So that's the origin of working on medical text, and I'll now present these slides. So first, I'll try to give examples. Of applications of natural language processing to text in the biomedical domain. So a first place where you find text in hospitals, that's in the patient records. When a patient goes to the hospital, they see a doctor, they get treatment, and then the doctors write reports. And this example is not in English, not in Spanish, in French, but well, to a computer that's the same thing, more or less. That is, that's just a large string of text. And just imagine you're a computer seeing something which looks like a string of characters, and you don't, well, as a computer, you don't really know what it means. So it's a bit the same maybe for you now with this text. And in this text, you might spot names here, like flecaine, Préviscan, and these are actually drug names. And you see there's also an amount, a quantity of drug here. 1 CP means a tablet, one piece. And this is morning and evening. And then another drug name, and another drug name here, once a day. So one type of task that you can try to do from this text is to try to convert this text into a table, a relational table like here, where you would find, well, you would like to have all the drugs, all the dosages, all the frequencies. So for each drug, flecaine, here one tablet, the frequency, morning and evening, and again, Previscan, well, nothing with it, so no, and so on and so forth. So these entities, that's a basic way of finding information, basic information in the text. So what I'm talking to you here is not really a deep understanding of the text, but only finding basic information in that text and extracting this information and putting it into a table. And then once you have a table, well, you can do computer science in lots of ways. You can count things, you can aggregate things, you can do statistics, you can provide that information in a different way, display it, and so on and so forth. So basically here, the initial specifications are, you give a schema where you have entity types. So here we have drug, dosage, frequency, and relations between these entity types. That is here, a dosage and a frequency can be associated to a drug. And then you need to find a way to do this automatically, that is to spot these words, these terms, and put them in the table in the right place. So that's information extraction. That's more specifically named entity recognition, finding expressions that describe a drug here, or a dosage, or a frequency, and finding relations between them. Now I'll turn to another type of task. I have here, well, actually that's a death certificate, so that's not so funny, but still that's a document, and that exists in all countries. So in this document, so somebody died, and then the medical doctor writes a very short report that states the reasons for the death, that is the diagnosis, the diseases that led to the death. So that's the final diagnostic, rupture of myocardium. So myocardium, that's part of the heart. That's actually the muscle in the heart. And that was that took place after an acute myocardial infarction, which took place in the context of a chronic ischemic heart disease. By the way, below you have the Spanish versions of these things, which are, to me, as complex as the English version, or the French version, by the way. So here the task is given one expression of a diagnosis here, so given a line of text here, to determine which category, which class it belongs to. Actually, there's a long list of diseases in the International Classification of Diseases with 11,000 classes, about 11,000 classes. And based on this text, well, here the US government, but it's the same in France, I guess it's the same in Peru too. The health ministry wants to collect data on causes of death. And for this, the data should be normalized, should be standardized. Standardized using the International Classification of Diseases, ICD. So the role here of natural language processing is to start from this expression and find the right disease in the long list of 11,000 diseases. And this one, rupture of myocardium, is actually named this way in the International Classification of Diseases. So you can see it in Spanish here, ruptura de la pared cardíaca, and so on and so forth. And well, it doesn't say exactly rupture of the myocardium. It says rupture of the cardiac wall, which happens to be a part of the myocardium. So it's not always easy. Sometimes it's easy, like here, chronic ischemic heart disease. Well, that's the exact name of that disease in the, well, nearly the exact name of that disease in that classification. So that's not too difficult. But for the first one, that's a bit more difficult. So that's a task where you have one line of text and you need to find one class among here 11,000. So that is text classification. You're given a text and you need to find one label among, well, maybe a few labels, or maybe among many labels like here. Text classification. here is another instance of text classification. The input here is this title and abstract. That's the abstract of a scientific paper in the medical domain. This is found actually on Medline, the large online medical library from the United States. And given this text, we would like to be able to find concepts that best describe the main topics of this scientific paper. So for instance, that was about avian influenza, and it talked about contact tracing, disease outbreaks, infection control, and so on and so forth. So by reading this text, you might be able to find these topics, not necessarily exactly with these names, but again, the task is to start from this text and find these categories. And here there are how many? 25,000 categories. So that's also a long list. That's a difficult task. By the way, currently this is done automatically at the National Library of Medicine by a text classification system that takes as input these texts, that is title, abstract, and find the most relevant descriptors like here for this text. And then this is used to search the literature. So that's for the library system, the online library system that many medical researchers around the world use to find relevant papers for this or that disease or other things. Well, another example of medical text, that's more like on the internet, where you have patient forums, and people say, oh, I've taken this drug, I have this disease, I've taken this drug, salazopirine, and well, I get pains because of the drug during the night. And that's the side effect of the drug. So here people are expressing the adverse effect they received, they experienced when they took some drug. And so it would be very interesting to be able to analyze this and find these adverse effects and then report them in the database to complement the existing national databases of side effects of drug. So that would be again a text classification. That's another example where you have a virtual patient here who is, that's a thing, designed to train a medical doctor, to train a medical student who is learning to interview a patient. And so this patient actually is a dialogue system, a fully automatic dialogue system, and it embodies a given disease. Here I think that's a back pain for something, and then the red is the patient, and the white is the medical student who is asking questions from the patient, from the virtual patient who is answering. So that's a quite different type of task, that's dialogue. And but that's very helpful too for training medical students. By the way, this is a system that we created about a bit less than 10 years ago, before the LLMs. Medical texts are not always easy to understand for us non-medical doctors. So, for instance, in this text, there's this repeat EGD, whatever it means, and it could be useful to have a way to, just click on EGD and find its definition like here. So that's something that's not too difficult, but still, it has, in the past, it has been the source of research to find ways to detect acronyms or terms like here and find their definitions, and then if you have this, you can propose these expansions. Well, there are many more use cases of performing natural language processing on medical text to help medical doctors, to help patients, to help translators. So here today I will focus on two tasks. One is text classification, and the other one is named entity recognition. So I will focus on them. I'll first define them, give examples, and then tell you you what methods have been used in the past and are used now also. So information extraction, which includes name entity recognition, has been the subject of lots of work and research. And one way to see this is to look at the number of shared tasks, that is, international challenges that have been proposed to research teams. So each of these points is a data set, a team that organized an international challenge in which they said, okay, we have this data. Let's say, well, an example would be this, and that has existed also. So we have this data, titled an abstract. Well, here is what you should find for this title and abstract, or these mesh descriptors. Well, please come up, if you're interested, please come up with a system that could perform this task as best as possible. And, well, next year in March, we'll give you a new data set with no solution, and you'll have, let's say, 3 days to run your system on it, return the results, and then we'll score the results. We'll tell you whether it was good or bad. And, well, several dozens of teams do that around the world. And then at the end, next year, we have a workshop where we compare the methods, the solutions, what works well, what works less well. So that's what a shared task is. And nowadays, every year, there are lots of shared tasks on natural language processing, on medical language processing. And, well, at some point I compiled that list, but there are too many now. I stopped in 2018 because every year there were more and more. The blue ones, on the top, that's biomedical, that is analyzing text from the literature, from the scientific articles, like the example I just gave. And the ones in red below, that's analyzing text in patient records. And maybe you're wondering, well, this started later. Why? Both are medical text. So do you have an idea why people started later to have shared tasks on patient records? What might be the problem with patient records, with text in the files of patients in hospitals?
Privacy, risk.
Yes, exactly. Privacy. That is, well, the text in your patient record that contains medical information about you. That's sensitive information. You don't want everybody to know that, I don't know, you have cancer or AIDS or something. So that's very, very private, that's confidential. So nobody else than you should know about it. You and the medical doctor who treats you. Even another medical doctor from elsewhere, if he's not treating you, he shouldn't know. So you cannot distribute such text. So that's why it's difficult to do anything on it. And to do research on it also is very difficult. So the first thing you need to do is to try to remove any identifying information, so the names of the patient, the dates, the birth date of the patient, and other things like that that might be identifying. So the first years when there were these shared tasks, the exercise, the task was to remove identifying information such as patient name and the rest. So, in summary, biomedical texts contain information about patients, information about diseases, knowledge, well, when it's scientific paper, they contain knowledge about diseases, drugs, treatments, and so on. So, but that's only text, and the goal of natural language processing of this text is really to extract this information, extract this knowledge, and put it in a way that's then machine readable, computable, such as tables, structured tables with normalized information. Yes. So the first task I will address is text.
Sorry, Pierre, before you proceed, because I had a question previous to this one. So you were talking about privacy,
Yes.
and then in 2007 they started doing challenges or a shared task on
Yes.
patient data. So you mentioned that they were removing identifiers, right?
Yes.
So that is a was a manual that I imagine that.
So I think you're referring to kind of chicken and egg problem where you need at the beginning to do something manually to remove the identifiers, and then you can start to design methods to do it automatically, and that's right. That's the way it worked. So initially, for instance, for the first one, they were removed manually. In I2B2 also, but actually what they did was, before they started this, they already worked on a de-identification system that they applied to this text, and then they checked it manually. So it was automated plus manual verification.
And the last one is, sometimes you remove information, private information as well, but how that affects as well the remaining information and the quality of what you have inside.
So there's a risk that if you remove too much information, you might, by mistake, remove useful information. Or also if you remove, let's say you remove all dates, that might also be a problem because dates are very important. The chronology, the succession of events in a medical record is important. So that's right, that's kind of balance that you must strike between protecting the privacy of the patients and keeping information that's useful enough. So yes, that's a difficulty. So there's no perfect solution, and removing information always has the risk of removing useful information from a medical point of view. Also, I should say that when you remove directly identifying information, that's not enough to make the text freely distributable, because that removes the easiest way to identify a patient, but there might be indirect ways. Let's say you have a patient who has a special profession, that's very rare, then it's easy to identify that patient. Or if you have a specific combination of events that occur to that patient, a specific disease plus a specific treatment, maybe at a specific time, then that's also a way to identify the patient. So these de-identified texts are not what you can call anonymous. Anonymous means you cannot find the person in any way. You have removed everything that could lead you to identifying the person. So that would be anonymous. But here what I'm talking about is really what's called sometimes pseudonymous. That is de-identified, you've removed directly identifying information. So the result is that these de-identified texts still need to be protected. That is, I cannot come here and show you a de-identified text or give them to you. They need to remain in protected places, typically in the hospital, and that still makes things difficult for research.
Thank you.
Welcome.
About all the patients that said, like for example, I'm going to be a volunteer for my information. I'm going to be provisioning display. In that case,
yes, that's a very good point. So a patient can volunteer to make their information, let's say, public or usable for research, for a certain research. And very often in hospitals, there are posters that say, well, if you don't oppose, we will reuse your patient records for research, for medical research. But then what I do is natural language processing research. That's different, so that's not covered. So for this, it would be possible to have a poster that says, we will reuse your data for medical research, natural language processing research, and then that would be okay. But that's not usually done in hospitals. But yes, that's a way to do it. And we should try to convince hospitals to do that so that we can obtain enough text to do research. I didn't fully hear what you said, but I understand that the point is, can you give guarantees of, let's say anonymity. Yes. So there's work on that also. Well, related to it's more difficult on text data than on structured data. Much more difficult because text can be interpreted in various ways, and it's difficult to pinpoint which part of text carries what kind of information. Well, the whole point of information extraction is to try to find out exactly what type of information is in the text, but only partially. So yes, it's still difficult to apply the same concepts, for instance, k-anonymity and things like that, to text. There are currently methods, there are also methods of, so what is that called? When you blur the data and in a way that's, or differential privacy. So there are currently large language models that are trained in a differentially private way. So there's one that just was published by Google 2 weeks ago, and they explain that if a fact has been seen in one text only, in one let's say sentence only, then it's not recorded. But if it is seen in two different texts, then it is recorded. So that's one way to do it. But then, how can you apply this exactly to the protection of patients? Because one fact, you have many facts about one patient, and typically one fact will be repeated in several parts of the report or in several reports. But yes, these are very interesting directions, and there's both basic research and applied research to be performed to be able to deal with this in a satisfactory manner. But yes, that's a key question when you want to work on medical text. Access to the text is very difficult for us to, as researchers, even with collaborations with hospitals. Okay, text classification. Well, you've seen this example, that's one. That just to remind you, you've seen this example too. So I'm showing you a slightly different example where this is part of a radiology report, radiography report, where it says that, chronic appearing linear filling defects. They are describing things seen on a radiography image. And then the classification task should say whether this is a positive example, that is, there is a problem. The radiography is showing a medical problem in the patient or not. So here below, they say there's normal opacification of the pulmonary arteries, etc. No evidence of pulmonary embolism. That looks good. So negative in medical terms means good, and positive means bad. If a doctor tells you you're positive, that's not good. Not like in real life when they say you're positive, that's good for you. Here it's not good. So the first one is a positive example. The second one is a negative example. And classification should be able to find which of these two labels should be attached to this input text. So how can you do that? Well, first, more precise definition. If you have an input text and the outcome is one of two labels, for instance, positive or negative, then that's a binary classification problem. If you have more than two labels, we call it a multi-class classification problem. So you need to choose one of them. Actually, binary is an instance of multi-class with only two classes. And then there's something quite different, which is that you have one input text, but you might have multiple output labels. So the text can belong to several classes, several categories. Just like here. Here you have one input text and multiple topics, multiple output categories. So that's a multi-label classification problem. That's the here. Then there's a question of how do you evaluate the results. That is, let's say you design a system that's able to classify these radiology reports. And the system works, so you run it on, let's say, on 100 examples. And it gives you, good predictions often, but sometimes bad predictions. bad labels. So how do you score it? So for this, you need to consider, well, this schema here. In this schema, you have what's your, well, in blue, the set of positive examples, the set of radiography reports with that correspond to positive cases, that is cases where there's actually a medical problem on the radiograph. So that's the blue set. And then what does the system say? The system predicts some outcome, some labels, and that's the, well, pinkish set. So in this set, the system said it's positive. But as you can see, it was not always right. It was right in this intersection of the two sets. And that's the cases that are called the true positives. That is, the system predicted positive, and that was right, that was true. So TP for true positives. Here, in that right side, the system predicted positive, but it was wrong, because that's not part of the blue set. So that's the false positives. And there are parts that the system did not predict at all, but that were true, actually, that were positives. So these are the false negatives. The system said, no, there's no sign here, it's a negative case, but in truth, it was a positive case. So that's an error also, a false negative. And well, outside of these two sets, neither the true cases nor the cases that the system predicted positive, well, that's the true negative cases. That is, cases where there's no problem, there's no defect on the radiograph, and the system did not predict it. So the system said it was negative, so that's the true negative. The system was right here too. So I've put these 4 cases in this matrix, in this table. So the truth here, the positives and the negatives, what the system predicted, the positives, predicted negatives, and the intersection of these, so the true positives, the positives that were wrong, so false positives, and then what should have been positive but were predicted negative by the system, so false negatives, and the actual negatives that were correctly predicted negative by the system, the true negatives. All right, so what do we do with this to give a score? Do we want to count only the number of true positives, or to divide this by the total number of examples, or something like this? So there are several ways to look at it, and that gives you as many scores. So one way to look at it is to say, okay, there was a number of true cases where the radiograph was positive. Among these, did the system find them? And we know that the system found the true positives, but not the rest. So if you divide the proportion of true positives among these, among the true, that's this ratio called recall. All right, so that measures how well the system finds the positives that exist in truth. Then if you can say, okay, the system tells me something, can I trust it? So the system tells me there are this set of positive cases. How often is it right when it says that? So how often is it right? What's the proportion of true positives among that set? That's true positives divided by this full set, true positives plus false positives, that's here. True positives divided by the full set. That's what's called precision. So a system that is precise, you can trust it. When it says something, it's usually right. But well, some systems can be very precise, but they don't say much. They are not very talkative. They say, most often they say, no, that's not positive. But when they say it, they are pretty sure. So maybe they get 90%, 95% precision, but they might be very bad at recall if they are very cautious and don't answer positive very often. So what you would like is a system that is both very precise, that is when it says positive, usually it's right, but which is also has also a very good recall, that is it does not forget too many positives. So you would like this intersection to be as large as possible among these two sets. That is, it should cover the true cases as much as possible to get a high recall, and the true positives should cover the predicted as much as possible to get a high precision. So if you want to have both at the same time, you can design a score that takes them both into account. That's a kind of average of precision and recall. Well, average, that's one way to do it. There's another average here, which is called the hyperbolic average, hyperbolic mean. And for this, you take the inverse of precision, the inverse of recall, you compute the average, and you take the inverse of it. So that's the inverse of the average of the inverse. And the property that it has is that if either of these two scores is low, it will draw the hyperbolic average below 2. So, and you can see, if you look at the derivation here, its value can be also seen to be twice the true positives divided by twice the true positives plus the rest of the sets. So it's close to the proportion of true positives among the union of the two sets. So that's why it takes into account both. It should be as large as possible based on the union of the two sets. All right, so these three scores focus on the true positives. That is, how often does the system find the positive cases. But so that's usually the most interesting, but sometimes you are also interested in the true negatives. That is, here the patients that don't have a problem and that the system identifies as patients that don't have a problem. So that's the true negatives. And there are measures that take into account the true negatives too. For instance, accuracy computes so both true positives and true negatives, that is all cases in which the system is right, among all the cases. So that's accuracy is a very simple metric. It's the proportion of cases where the system is right, whatever positive or negative. So accuracy can be useful in classification, but it's if the classes are imbalanced. That is, if one class has very few cases, let's say there are very few positive cases. And that's usually the case, well, that's often the case in medicine. You have few patients that have the disease, and that's fortunate. And many patients don't have the disease. So in that case, if you compute both the true positives and the true negatives are easy to find. That's nearly all the patients. So if you compute their sum, you're likely to have a very high score, because the system will easily find the true negatives. So if your system, or let's say you have a case where the disease or the problems here for radiography occur in only 10% of the cases, and let's say your system always says no problem, always says negative.
Terrible.
Then how often is your system right? There are 10% positives, and it says 100% negative. How many negatives are there? 90%? Yes, 90%. And the system will be 90% right. Not bad, 90%. If I say I went to this exam and I got 90%, well, I'm good. Well, this system is silly, always says no. So we shouldn't give it a high score. Well, if instead of accuracy in that case you use F1 score, well, the system never found the positive, so it has 0. And that's it. So you see, depending on the score you use, you might give a very high score or a very low score to a system, especially in imbalanced situations. So choosing a score is very important to evaluate a system, because you might be developing a nice system, and then you choose the wrong score, and it gives you wrong feedback on the quality of your system. Well, to make it more complex, if you look at the Wikipedia page on confusion matrix, you'll find many more scores that may be relevant in different situations. And among these, you find the precision, you find recall, that's also called sensitivity, and you find accuracy, and you find F1 score, but you can see that there are many others. All right, back to text classification. So, as said, text classification, you start from a text, and you want to detect whether that text is a case of positive or negative class. For this, what we usually do is that we start by modeling the contents of the text and obtaining a representation of that contents. So we don't take the string of characters directly and put it in the machine, but try to find out what's in this text first. So that's called modeling the text, and the result is a representation of the text. Sometimes that's called features, that is various characteristics of the text. And then based on this, you design a decision rule that, based on these features, will tell you whether it's positive or negative. So for instance, starting from this small text, one standard way in plain natural language processing is to, divide this text into words. First maybe you see chronic has an uppercase C, it doesn't make specific sense, so you just kind of bluntly convert all uppercase to downcase. Okay, then you split into words. So there are issues at each step, but I will not detail them. It's not so simple as it seems. So you get a list of words, sometimes called tokens, that is elementary units. And then, some of these words are not so useful from the point of view of contents of sense. For instance, of, the, are just kind of auxiliary words, grammatical words. Sometimes we call them stop words, so we remove them. Sometimes, for instance, in Spanish, you may have diacritics such as complicación, and sometimes people write the diacritic, sometimes people forget it. So maybe it's not so important, or at least it's easier maybe to just normalize the words and just remove diacritics. Sometimes it creates ambiguities, but most of the time it's fine. And then, in some languages, Spanish, English a bit less, you have what's called inflection. For instance, in English, defects can be plural, to fear can be with German form, arteries, that's again plural. So the normalized form, the form that you find in the dictionary, will remove all these variations. So you normalize the words to have a more standard, a more regular description of each word. And then, I'm stopping here, but you might do more. And so instead of having this string of characters, now you have a list of words. And you can start to test words in this, whatever the initial form, so you don't need to know whether the effect was singular or plural, etc. And here I've written a very simple, silly rule that says if chronic is a member of this word list, then the result, the class should be positive. If normal is part of this word list, the result should be negative. I've chosen these two words because if you go back to this example, here you have chronic, there you have normal. So it will work, my rules will work on these two examples. That's not too strong, but that's just an example. So you see that you can design rules like this manually, based on your knowledge, your understanding of this text. Then, something we often do is, instead of looking at every word and trying to design rules like this, we can try to turn this into a numerical representation by creating, well, first compiling all the words that are used in all these texts. So you get a vocabulary set. And then, in each text, you build a vector that tells you whether a word occurred in that text. And so that creates a matrix where you have let's say in the rows you have the text, in the columns you have the words, and you put a 1 if a word occurs in a text. And then to represent one of the texts, you just extract the row for that text where you have a 1 for each word that occurred and a 0 for the other words. So that gives you a vector for each text. And then based on this vector, you can try to do things more automatically, such as, well, for instance, you might have, let's say you have the vectors of all the positive examples. Maybe you can take the mean of these vectors, and that's a kind of prototype of the positive example. And you can take all the vectors of the negative examples, and maybe again compute the mean of these vectors. That will give you a prototype of these negative examples. And then when you have a new text, you compare this vector to the positive prototype, you compare it to the negative prototypes, and you choose the one that's closer to it. So that's one way. There are many other ways to do it. And actually, what you are starting to do there is to use supervised machine learning. That is, you're using the examples of text. So here I'm reproducing a picture from that paper that showed how you can use supervised machine learning to classify radiography reports. So you convert each of the examples, each of the text into that vector that contains 1s for words that are present and 0s for words that are absent. And you associate to it a label, that's the positive class or the negative class. So these examples are positive, those examples are negative. And based on that, you use a supervised machine learning algorithm. Well, there are many out there. Naive Bayes is an easy one. Support vector machines is another one. Maximum entropy or logistic regression is used a lot. And based on that, well, what's happening is this. You have the input text. You have performed that feature extraction that gives you a feature vector for each text. You have the labels. They are called gold labels here because that's the true classes for each of the examples. And based on this, you can train your machine learning system that will learn a model. The model will be a function, a hypothetical function, an approximative function that, based on the input features, will predict a class, a label y. So y hat, because it's estimated label. So the model is stored, and then when you have a new text, you perform feature extraction again on the new text, and then you use that function in inference mode, that is, based on this function and these features, you compute the predicted class for that new text. So that's the basic mechanism in supervised machine learning. So for this, you need to have the input text and to have the gold labels, that is, to have the true labels for each of these texts. And of course, you need to have positive examples and negative examples. More generally, you need to have examples of each of the classes that you are considering for the classification. So binary classification, 2 classes, positives and negatives. Multi-class classification, maybe classes 1, A and B and C and D and so on. And you need examples for each of these classes to train the system to obtain a model that's suitable for all these classes. And I've said also that there's a variant that's multi-label classification where you need to produce multiple labels for each text, for each input. One way to do this is simply, for instance, to have a different classifier for each of the labels. But there are more ways to do So, as said, you have this input text and you perform feature extraction, you compute a vector there. And this vector, I showed you the simple method that consists in just finding which words are present in the text. And you then assume that these words will be good clues for the classes. Yesterday morning, you had a course on BERT, on transformers. So what do you remember of transformers? Transformers, you can give them a text as input. There's a tokenizer that splits the text into words. And these words then obtain input embedding, input vectors. And these vectors then are passed through layers and layers of transformer, that is cross-attention, self-attention layers. And this repeatedly in such a way that for each of these input words, in the output layer, you have a vector that represents these words in the context of the full sentence, of the full text.
Oh.
And among these output words, you have output vectors. You also have one for a specific marker that's called the CLS token. That's added to the beginning of the text, and there's a seek token at the end of the text. But the CLS token at the beginning of the text, it plays a very special role. That is, it is there to kind of represent the whole text. So it's a contextual embedding, a contextual vector, a vector that represents the contents of the whole input text. So, instead of computing a vector that just says this word was there, this word was not there, you can use a transformer. You can use a neural system, here a transformer such as BERT, to which you provide the input words, the input text, and then you run it, and it provides as output, well, one vector for each input text, input word, but also the CLS vector that represents the contents of the full text. So this CLS vector you can use as a feature vector to represent the input text. So what's in it? We don't know exactly. I mean, these are 768 dimensions with the base BERT. And these dimensions, we don't know what they represent individually, but what we know is that globally, they give quite a good account of the contents of the text. So we can use this as the input to a classifier and train the classifier in the same way as I was describing previously. That is, well, we take the positive examples, negative examples, and feed them to the classifier this way, train the model. So the model here is an additional layer. It's another thing. It's not BERT itself. It's a classifier that we put behind BERT, just like here. You see, you have the input words, the input tokens here, the input text. You run BERT, and in the end, you have this CLS vector that represents the contents of the full text. And you pass this to a linear neural layer with a number of outputs that is the number of classes that you have. So binary classification, this layer will have only two outputs, two output neurons. And then the classifier, this layer will give a probability for each of these two output classes, and you choose the one with the highest probability. So here the decision rule is just choose the class with the highest probability. And the encoder here, the performs feature extraction, and that's the most important part finally. That is, it transforms the text into a vector that represents its contents in a quite good way. And then the job of the classifier is easier because of that. Alright, so that was BERT used as feature vector extractor. here, usually you have this encoding, you convert the text to a vector, and then you have vectors for each of your input examples, each of your training examples, and you train the classifier based on these vectors. But when you have a neural architecture like this, with the transformer layers here, and then the classifier, which is actually a linear layer, and also in the neural environment, what you can do instead of just training the linear layer here as a classifier, you can also retrain the weights of the transformer. That is, the transformer is producing a vector that represents the text, and you train a classifier to classify this vector as best as possible into the two classes. But at the same time, you can try to improve the representation that's produced by birds to make it even more suitable to this specific task. So that's what's called fine-tuning the weights in the transformer. That is, you don't want to change them very much, you just want to adjust them a little bit, to tune them finely. So to move them a little bit, but not much, because if you do it much, then you will lose what has been learned by birds previously. So you fine-tune the bird weights at the same time as you train the classifier, so that the output representation of birds is really fully fit, fully suited to that classification task. So that's what's called fine-tuning. Supervised fine-tuning, that is, you fine-tune the weights of the bird transformer for this classification task, supervised by this classification task. Alright, so for text classification, I think you'll have more about this tomorrow evening with Diana. I think Diana is giving a course on fine-tuning large language models, including for text classification. So probably she will tell you more about both fine-tuning birds and also using an LLM to directly ask it to perform the classification. So I still have some more, but maybe I say a few things about entity recognition, or I stop here, as you wish.
I mean, it's up to you, but I mean, you can.
Yeah?
Sure.
Okay. So in entity recognition, I've shown you this example. You remember that's extracting specific pieces of information from the text. So to give you a simpler example, let's say you have this sentence history of hypercholesterolemia and type 2 diabetes mellitus, where you have here two diseases, signs, symptoms, two diseases.